just going over some vocabulary that you might know or might not know. But I feel like because of all the breaks we've had, we need to kind of like get our vocabulary straight before we keep going in this unit. So we're going to go over a bunch of vocabulary for polynomials, starting with the y-intercept. The y-intercept is where the graph crosses the what? Oop, the y-axis. So y-intercept is the y-axis crossing point. There should only ever be one. If you have more than one, something wrong happened. It's not a function anymore. On this graph right here, we're just going to label some stuff. Your y-intercept, again, is where the graph crosses the y-axis. So you have a little coordinate point here where the graph crosses the y-axis. That's called the y-intercept. We feel good about the vocabulary word. How about the x-intercepts? It's where the graph crosses the x-axis. It is crosses or touches the x-axis. So how many do you see in the picture here? 2. There are 2 places where it touches or crosses the x-axis. So we're going to label those x-intercepts. But we're going to get a little bit more detailed now that we're doing higher ordered polynomials. Specifically, we're going to talk about what are called repeated solutions. What does the word repeated mean? Like more than once, the same thing happening more than once. When you have a repeated solution visually on a graph, what that means is that the graph bounces off the x-axis instead of crosses the x-axis. So do you see how the first x-intercept we run into right here, how that bounces off the x-axis? That means that that x-intercept is actually a repeated solution. I'm going to use the shortening RS for repeated solution because that's way too many letters. Is everybody okay with RS meaning repeated solution? That means there are actually 3 solutions for this graph because there are 1, 2, 3 places it crosses or touches. Repeated solution means 2. It's bouncing. Now this next vocabulary word is a little bit more advanced than we need, but it's pretty cool, so I'm going to teach you about it anyways. It's called multiplicity. Say that word to yourself. Multiplicity. I didn't hear you. Multiplicity. Try saying it, because you're going to say it wrong the first time. Multiplicity. Try it. Everybody try it. Multiplicity. See, it's weird the first time you talk about it. Multiplicity is talking about the power of each factor. Factors are in parentheses. So if I were to zoom in on this little example we have here, do you see how this first parenthesis has a power of 2? And how this second parenthesis has an invisible power? What's the invisible power? 1. So we have 2 multiplicities. Any even multiplicity, like a straight up even odd number, that means that that 0 is going to bounce off of the x-axis, making it a repeated solution. If it is an odd degree or an odd multiplicity, that part is going to cross the x-axis. Now this is actually the function. It gives you the picture on this page. So if you notice, the -3, which comes from this parentheses, opposite sign, it has an even multiplicity, so it bounces. This one, +2, has an odd multiplicity, so it crosses. Now, multiplicity, I'm not going to ask you a lot of questions about it, but if you end up taking pre-cal, I teach that class, it's a huge deal. So knowing just a little bit about multiplicity beforehand is going to be very helpful. Bouncing and crossing. Okay? Moving right along, this next little section already has most of it labeled for you, but we're going to use those highlighters here. When we're talking about an increasing interval, we're talking about the x values where the graph goes up. So if you were walking along the graph, you're just trying to identify the sections where the graph goes up. Would you agree that this section right here that I'm highlighting in green, which you can too, that's going up, like it would be walking uphill, correct? And then also, if I look at this section, isn't this section also going up? So this graph has 2 increasing intervals, 2 sections where it's going up. A decreasing interval is just the x values where the graph goes down. So pretty obviously, in between those 2 green sections that I just highlighted in there, you have a section that's going downhill. That's a decreasing interval. So we're talking about where the graph would be uphill or downhill if you were walking across the graph. Does that make sense? Actually, answering these questions is a little difficult because the notation is weird. So we're going to do that not till next class. But just since we have these notes in front of us, it'll be really helpful if we have the image for interval notation here later. So everybody draw the following with me. For these two symbols, it is an open circle or a parentheses, as well as the infinity sign. Does this look familiar? Have we seen this before? Yeah. Then you have the symbols with the line underneath it. That goes with a filled in circle and a bracket. Again, we're not going to really answer questions about this today, but since these are the notes that will help us for next class as well, we're going to go ahead and put that there. That will eventually help us actually answer increasing and decreasing interval questions. In the same idea of increasing and decreasing intervals, we have a new vocabulary word that is named very nicely. It's called turning points. What do you think happens at a turning point? Exactly, it turns. The graph is going to turn twice in this picture. Do you see how it was going up, then it goes down? That's a turn. And it's going down, and it goes back up again. That's another turn. Turning points are the overhead umbrella term for local maximums and minimums. A local maximum is going to be a hill, and a local minimum is going to be a valley. Now, they're called local maxes and mins compared to when we just said max or min because it's not absolutely the max or absolutely the min. It is just locally the maximum or minimum, meaning if you look at this point right here that's labeled local maximum, is it the highest the graph goes, period? Isn't the graph bigger over here? So it's not the absolute maximum, but compared to the stuff next to it, isn't it the biggest point? So it's a local or relative maximum. Same thing here. This is not the lowest the graph goes, period, but compared to the stuff around it, it is the lowest it goes. So they're hills and valleys, but not the largest hill or the largest valley. Makes them local maxes and mins. But every turning point is actually either a local max or a local min. Or sometimes an absolute max or min, depending on the graph that we have. But we're going to usually stick to the locals. Does that make sense? Why we added the word local there? It's still the same idea of hills and valleys, but it's not the absolute hill or absolute valley. The last new piece of vocabulary is even versus odd functions. Now, I'm not talking about even and odd in the sense of like even numbers and odd numbers, although that kind of plays into it a little bit. Even and odd in algebra and on a graph talks about symmetries on the graph. So I want you right now to take one of the highlighters and I want you to highlight the y-axis on this very first graph. So highlight the y-axis, that's the up and down axis. If you were to fold that first graph perfectly along the line you just highlighted, what would happen? If you were to fold it right along there. What would happen to the shape of the graph? It would line up right on top of itself, right? When graphs can be folded along the y-axis and land right back on top of themselves, they are called even functions. So we are folding along the y-axis. If you can fold it like a book and they land right on top of them, they're even. We're not necessarily talking about the degree, we're talking about the shape. Is it even? Odd functions are not a fold anymore. For odd functions, they're symmetrical about the origin. And what that means is that we put a pin in the origin, like hold the graph at the origin, and we spin it 180 degrees. If you were to take this graph and put a pin right here, and then spin the graph around like this, everybody look for a second. Wouldn't this curve land right back down on this curve? So by spinning it around the origin, we have symmetry. That is called an odd function. The way I remember this, odd and origin both start with O. Great. odd origin, even y-axis. So this is like a rotate 180 degrees, and even is like a fold. It doesn't necessarily, again, have to do with the degree, like the power, but it has to do with the visualization of the graph. There is an algebraic way to talk about this, which I have on your paper. I'm not really interested in that for this class. Again, in pre-cal, we'll be doing it by hand. But for this class, we want to look and see if we can visually tell if something is even or odd. Woo, that's a lot of vocabulary, right? So we're going to start learning about the fundamental theorem of algebra, but don't overthink it. It sounds really fancy, but you actually already kind of understand this concept based on what we did the last time we had like a normal class day. And you're probably thinking to yourself, we've taken algebra and we've taken most of algebra 2. How are we only now learning about what's called the fundamental theorem of algebra? It's because it's kind of complex to begin with, but its use is very simple. If you were to read the fundamental theorem of algebra off of a math textbook, here's what it would say. If f of x is a polynomial of degree n where n greater than 0, then the equation f of x equals 0 has at least one solution in a set of complex numbers. And I'm sure your brain just totally tuned that out. So here, let me translate for you why this is important. In other words, a polynomial of degree n has exactly that many solutions every time, no matter what. And it has a max of just one less than that turning points. So what happens here, because of the fundamental theorem of algebra, is we're going to be able to very quickly determine how many real and how many imaginary solutions exist for all of our polynomials. Because the fundamental theorem of algebra tells me how many I should find, and a visual graph tells me how many real ones I see. So we're going to take this case by case. For quadratic functions, which are x squared functions, what's the degree? Ooh, what is a degree? You know this, you just forgot because we've had 4 snow days. A degree is the little floaty number, but the largest little floaty number. So 2, x squared has the power 2, so it is degree 2. By the fundamental theorem of algebra, that means how many solutions does it have? 2. And what is the maximum number of turning points? Ooh, 1 less than it. 1. It has the maximum of 1 turning point for a quadratic, which makes sense. So if we were to look at this first example, do you see it crossing or touching the x-axis?
Yes.
Yeah, you see it crossing or touching right here, but here's the thing. I'm telling you right now there should be 2 solutions. You only see one of them. What's happening here? It's a turning point. Good vocabulary. There's another vocabulary word from the other side that's happening here. It's in the top section of our vocabulary list.
Multiplicity.
It has to do with multiplicity, sort of, but look right above that.
Repeated solution.
A repeated solution. Isn't that bouncing off the x-axis? That means,
How do you know it's bouncing?
like, I mean, look at it. I don't know how, I mean,
It's not bouncing.
well, it's not crossing. It would either cross or it will touch and bounce off. No, it's not going to look like a straight up bounce, you guys. It's going to be like boop, boop, like it touches it and it goes back the same direction. We're calling that a bounce. Since, like a little trampoline, like since this bounces off the x-axis, we know that that is a repeated solution, which means there are 1, 2 solutions at that point. Fundamental theorem of algebra tells me I should find 2 solutions. Did I find them all? Aren't they? They're both right there because it's a repeated solution. In this second example, how many solutions do you visually see?
0.
0, because check this out. Did anything cross the or the x-axis there? No. So before today, you would have answered no real solutions. And we've been telling you to answer that because we have to get to the fundamental theorem of algebra. I still know there are how many solutions based on the degree. There are 2 solutions, and if they're not real, what do they have to be?
Imaginary.
There are 2 imaginary solutions here. I know there has to be 2. So if I don't see 2 real ones, then they have to be imaginary. Now, I'll be honest with you, I accidentally copy-pasted the same graph on here twice, so I need you to change yours. I'm going to actually white mine out, but I know you don't have white out. So instead, I want you to draw in a graph that looks like this. Specifically so that it has how many solutions showing? 2. And I see that there are 1, 2 solutions. So I'm good because fundamental theorem of algebra tells me there should be 2 solutions. Okay, let's kick it up a notch. For our cubic functions, the ones in the middle, what's the degree of a cubic function? 3, which means how many solutions should it have? 3, and a maximum of how many turning points? 2, just one less than that. That's what fundamental theorem of algebra tells me, and here's why that's important. If you look at that first example, it's a cubic function because it looks like a squiggly line. And we can see it cross or touch the x-axis how many times? 2. But I know there has to be 3 solutions, so where's the third one? Ooh, not a y-intercept. We're just looking at x-intercepts. The bounce. Remember, this is a repeated solution, so you have 1, 2, 3 solutions. So we're good. Fundamental theorem of algebra says I should find 3. I found 3. Awesome. How about the next one? How many zeros do you actually see?
2. I'm at 3.
3. We've got 1, 2, 3 real solutions because we can see all 3 of them. Fundamental theorem of algebra tells me there should be 3. I see 3. Awesome. Good to go. Now, how about the last one? I only see 1 of them, and there's not a bounce or anything. So what does that mean about the other 2 that I'm missing?
2 imaginary.
They're 2 imaginary. I'm going to start shortening the word imaginary to IMAG. Are y'all okay with that?
Yes.
It's just too long of a word. I'm too lazy. So fundamental theorem of algebra tells me I should find 3 for every cubic function. If you don't see all but 1 of them, first of all, maybe zoom out. But second of all, they're probably imaginary. Make sense? Okay, the last function we'll talk about are quartic functions. Just really quickly, what shape does quartic functions kind of look like? A W. It'll look like W's or M's if it's flipped over. That's going to be your quartic functions. Yeah, to McDonald's. What is the degree of a quartic function? 4, which means we should always find how many solutions? And a maximum number of turning points? 3. Okay, we look at the first one. We're looking for solutions or roots or zeros, x-intercepts. How many do you visually see?
3.
Ooh, x-intercepts only, guys, not y-intercepts.
Oh.
Only x-intercepts. Yeah, we see 2.
They bouncing.
But they bouncing, so what? There's actually 2 in each one. So 1, 2, 3, 4. Did I find all of them?
Yes.
Cool, great, awesome. What is this called again when they bounce? It's 2 words. Starts with the R.
Repeated solution.
A repeated solution. That's what you're going to see sometimes. If we look at the second one, we know there should be 4. How many do you see?
2.
2, which means what?
2 imaginary.
So we have 2 real and 2 imaginary. Because I don't see the other 2. Now what about the last one? 4. 1, 2, 3, 4. There are 4 real ones. Am I missing any? No, I'm good. So fundamental theorem of algebra allows us to quickly check to make sure we found all of the solutions, that we found all of the rocks words. Are there any questions about this before we go to actual practice problems? Okay. The first practice problem, don't overthink it. It asks you, how many total roots does this function have? Now you might be like, wait a second, Miss Quigley, you did not define the word roots on our vocabulary page. You're right, but roots is a part of 4 words that all means the same thing. What are those?
X-intercept.
Uh-huh.
And
Solutions. Your roots, zeros, x-intercept, solutions will interchangeably be the thing I ask you for because they all mean the same thing. Same question, just a different vocabulary word tucked in there. So if I were to ask you this, how many total roots does this function have? Now that you know about the fundamental theorem of algebra, you can answer this question like this. Because what's the degree of this polynomial?
3.
So how many solutions does it have?
3.
Done. That's the fundamental theorem of algebra. The only way I can make it harder is if I give you a question like B. Because what's the degree of B?
4.
4. Yeah, just truly remembering that the degree is not necessarily the first polynomial or first exponent, but the largest exponent. But if it is a degree 4, it should have 4 real solution or 4 total solutions. Now what about the last one? How many solutions will that one have? 5, because the degree is 5. Fundamental theorem of algebra tells me it will have 5 solutions. Great. Now this question is how many? If I were to ask you what are they, like what are the zeros, you would still want to make sure you found them all, so you check with the fundamental theorem of algebra, but you turn back to your notes of what we did last class to figure out how to find them, aka graph them and see where it is. So if it says what are the zeros, you find the actual numbers on the graph. If it says how many, you just do like we just did. Do you hear the difference in those two questions? Okay. Now the last little section, also very easy. The only way it can confuse you if you don't recognize the function you're working with. The question is still, how many solutions? Well, we need to know the degree to know how many solutions, but I don't have a formula here. So we got to start recognizing the shapes. What kind of function is this M shape?
Even.
Ooh, I'm thinking a quadratic cubic quartic.
Oh.
So the 3 columns at the top. What is this one? Quartic. The W's or the M's are your quartic. So let's just write that down since we're learning so that we remember it's quartic. Quartic are x to the 4th powers. So how many total solutions should I find? 4. How many do you see? 2. So we are going to have 2 real and how many imaginary? 2 imaginary. Because I see 2 of them, and I know there has to be 4, so 2 of them are imaginary. Now, what shape does this one kind of look like in the middle? Is it quadratic, cubic, or quartic? Look at the shapes at the paper. Does it look like a U? Does it look like a W? Or does it look like a squiggle? Squiggle. Cubic functions kind of look like elongated S's whenever they have big hills and valleys. This one is a really stretched out squiggle, but that means that it is cubic. Cubic functions are degree 3. So I should have a total of 3 zeros. How many real ones do I have? I have only 1 real, but how many imaginary?
3.
Ooh,
2.
2. Yeah, because we want a total of 3 of them. Does that make sense how you answer these? First, have to categorize what type of equation it is, but then you should know the degree. What type of function is this last one? Cubic again, very good, which means it's degree 3. And again, how many solutions do you see?
1.
1. So 1 real one, thus 2 imaginary. We couldn't have done this before we knew the fundamental theorem of algebra. Now, I'm not having you find imaginary solutions today. Ugh, kind of a hefty kind of problem. I will have you find real solutions, which means you just graph the function beep, beep, beep in your calculator and see where it crosses. Yes? So we're going to pause here right now, and we're going to practice this with our homework.